Hi, I'm Zor. Welcome to Unizor Education. We will talk today about systems of linear equations. As usual, we have to start with definition. Well, first of all, system of linear equations is a system of equations. And you know the generalized form of the system of certain number of unknown variables, in this case n unknown variables, and this is the system of m equations. This is a generalized form. So we have m conditions, m functions actually, of unknown variables, and I equalize them to 0. Now, so what is a system of linear equations? Well, obviously, each one of these should be a linear function of the unknowns. Now, what is a linear function of unknowns? Again, generalized format is the following. So that's the first equation. So the indices and the coefficients are, first index is equation number, and the second index is basically the variable number. In addition, I put index 0 for just a constant. Now, the second equation would be a 2,0 constant plus 2,1x1 plus 2,2x2 plus etc. plus 2n xn equals to 0, etc. And the nth equation looks like this. mn xn equals to 0. So this is a system of m equations with n variables, x1, etc., xn, and every equation is a linear function. Linear means every variable is basically just by itself, without any kind of additional manipulation with it, just multiplied by some constant. And there is one free constant. Now, alternatively, and actually in many more frequently occurring cases, the constant is actually shifted to the right of the equation, so it will look like this. This would be B0, B1, B2, Bn. Well, this is just an alternative form, exactly the same thing. B's are constants, each A is a constant as well. Now, can we consider any system of m equations with n variables that look like this a good and meaningful system of linear equations? Well, the answer is no. First of all, think about these coefficients. A very important quality for each of these equations is that at least some of these, at least one actually, of these coefficients should not be equal to 0. Because if everything is equal to 0, I mean all coefficients in one particular equations are equal to 0, then let's think about, if the right part is also 0, then you have 0x1 plus 0x2, etc. plus 0xn equals 0. Now, what is this? This is basically identity, and any combination of x1, x2, etc., xn would fit this particular equation. So there is absolutely no meaning in including this particular equation into the system. It doesn't add anything, it doesn't subtract anything. Whatever other equations produce would definitely fit this one. So we always assume that among these equations, which constitute a system of equations, we do not have this case. So in each equation, at least one coefficient is not equal to 0. And by the way, if the right part of this 0 equation is not equal to 0, then it's basically a meaningless combination, because no variables multiplied by 0 and summed together would give a non-zero number. So basically, it would constitute an absence of any solution, which is not an interesting case as well. Okay, so the first requirement is that for every equation, there is some coefficient which is not equal to 0. Okay, that's number one. Number two, and it's also very, very important, I would like to talk about linear independence between these equations. Here is what I mean. Consider the following system. Okay. Now, think about this. If we subtract from the second equation, the first one, x and x, x and minus x would nullify each other, z minus z would nullify each other, 2i and y will result in y on the left side, and 2 minus 1 will result in 2. So basically, this equation doesn't really bring any new information. It's derived, it's dependent, it's linearly dependent in this case, on the two other equations. Which means, basically, it's exactly the same thing as if I don't have this equation at all. And I have only two equations with three unknowns, which, as I mentioned many times in the previous lecture about the systems of equations in general, this is usually the case when we have an unlimited, infinite number of solutions. And basically, indeed, you can have the solution like this. X is equal to 1 minus 2, this is y, which is 2, and minus z. Y is equal to 2, and z is any. So if z is equal to 1, you will have minus 1, minus 1, minus 2. If z is equal to 100, you will get minus 1 and minus 100, so it's minus 101. So basically, infinite number of solutions with z taking any real value and x calculated based on z and y is equal to 2. Any triplet of these numbers which correspond to this will be a solution. Not interesting. So basically, we would like to exclude this case when one of the equations is a combination, a linear combination in this case, of the other. Now, I will spend a little bit more time later on in this lecture about what's the criteria of the dependency, but sufficient to say that we would like to have the system of equations linearly independent. Now, linearly independent in more strict sense of this word means that I should not have a linear combination of some equations to be equal to some other equation. Basically, that's what it means. Now, the last requirement which I would like to put on my system of linear equations. So the first one is at least one non-zero coefficient is in any equation. Number two requirement is linear independence. And number three, I would like to have the case when m is equal to n. So number of equations should correspond to the number of variables. Now, obviously, if m is less than n, as we saw many times before, we will have infinite number of solutions. Not interesting. Now, if m is greater than n, and system is independent, then most likely we will have a situation of no solutions at all. Not interesting neither. So this is a typical requirement for a system of n linear equations with n variables. So coefficients, at least one non-zero in each one of them, linear independence and the equality between the number of equations and the number of variables. So if our system of equations satisfies these requirements, then we will consider it as a meaningful, a valid system of n linear equations with n variables. And we can attempt to solve it, obviously. Now, it brings us to the concept of solution. How can we solve this particular system of equations? Now, I did briefly touch the method of substitution when I was talking in general about system of equations. In case of linear equations, and again, we're talking only about good, meaningful system of linear equations. Now, in this particular case, we can always use the method of substitution. Always. And it always works fine. Now, here is basically the simple example. X plus y plus z is equal to 6. X plus 2y plus z equals to 8. And 2x plus y is equal to 4. Now, what I would like to do is, I would like to solve this particular equation, system of equations, using the method of substitution, which is basically a straightforward method which does not require any ingenuity. You just know the algorithm, you know the methodology, just use it and you will get the solution. Now, how to get the solution to this particular equation? Well, again, the method is extremely simple. First, we use one equation, let's say the first one, and we express one of the variables in terms of the other variable. So, in this particular case, we can derive that x is equal to 6 minus y minus z. Right? So, by adding minus y and minus z to both parts, left and right, we get this. On the left we will have only x, on the right we will have this. And now we can substitute it instead of x to here and to here. Now what do we have in this case? Well, 6 minus y minus z plus 2y plus z equals 8. And 2x, which is 2 times 6 minus y minus z plus y equals to 4. Now, as we know is supposed to happen, the method of substitution in one step reduces the number of equations by 1 and reduces the number of variables by 1. So now we have only y and z and only 2 equations. Alright, now let's simplify this. Y minus y and y, it's one single y, minus z plus z, well, that actually nullifies each other, and the constant 6 and 8, so it's 2. Okay, the first equation, after simplification, gives immediately the value for y. That's good. Now, the second equation, minus y plus y, minus 2y, sorry, plus y, that's minus y, minus 2z equals to, this is 12, this is 4, so it's minus 8. Right? Okay, now, obviously we can substitute this 2 here, and we will have minus 2 minus 2z equals minus 8, or 2z goes there, 8 goes there, it's 6, z equals to 3. Okay, so we have y equals to 2, z equals to 3, and now using this original substitution, we can say that x is equal to 6 minus 2 minus 3 is equal to 1. So x is equal to 1. So my solution to this system of three equations with three unknowns is x equals to 1, y is equal to 2, and z is equal to 3. Now, if you check against this system these three values, and I don't want to do it, but you have to do it basically, you will see that this is the correct solution. So, let me summarize. What I did here, I have solved this particular system of equations using the method of substitution. I took one particular variable from first equation, expressed it in terms of the other two, substituted into the other two equations, getting only two equations with two variables, which turned to be a very simple one. And basically, even if it's more complex, I can do exactly the same thing again and again and again. On each step, I'm reducing the number of equations by one, number of variables by one. So if I initially have a system of n equations with n variables, after n steps of substitution, we can actually get to the solution. Straightforward, no ingenuity, lots of calculations. Granted. Now, let me try to use exactly the same method in a general case of two equations with two variables. Now, what is a general case of two equations with two variables? Here it is. ax plus by is equal to p, cx plus dy is equal to q. This is a general form of a system of two equations with two variables. Now, how can I solve it? Do exactly the same thing. Now, I know that at least some coefficient in every equation is not equal to 0. Well, let's assume for definitiveness that this is x, coefficient at x, which is a, which means I can find that value of x in terms of y. It would be x equals p minus by divided by a, right? Now, I substitute it into this, and I am getting only one equation with one variable y, which is c p minus by divided by a plus dy equals q. Multiply by a, open the parenthesis, cp minus bcy plus a dy equals aq, from which I can say that y times ag minus bc equals aq minus cp, from which y is equal to aq minus cp divided by ag minus bc. So this is the answer for y, and using this we can find the x. Y can be substituted to this. X is equal to a p minus by, and by is this, so it's ag minus bc, and b times y would be abq minus bcp. All right, equals. All right, common denominator above, so it will be AD minus BC, P times AD, so it's ADP minus BCP minus ABQ, and minus BCP. Plus BCP, minus and minus would be plus. So BCP is out, so I will have, and A I can factor out here. A dp minus bq divided by ad minus bc. I combined these divisions. A is also out, and this is my answer, basically. This is x. Now, what's interesting about this? Denominator. You see, I'm dividing by this, so it must be not equal to 0, right? So this is a very interesting condition. So if you have an equation like this, AG minus BC must not be equal to 0 for this particular solution to work. All right, just remember this particular property of the system of two equations with two variables. But anyway, the method of substitution gives you this solution in case when AG minus BC is not equal to 0. Okay, this is good. Now, but why and when AG minus BC is equal to 0? Well, you remember that in the definition of the system of definition of the good system of n equations with n variables, I suggested that it should be linearly independent. So my statement right now is that this particular denominator, being or not being equal to 0, actually means that this system is or is not linearly dependent, linearly independent. So if this is not equal to 0, this is linearly independent. And if this is linearly dependent, then this is equal to 0. Now, I can actually very easily prove it. Now, what does it mean that the system is linearly dependent? Well, it means that there exist some numbers u and v. So if I will combine my left parts with these u and v, I will get 0. That's what it means being linearly dependent in case of two different equations. Because, as you understand, if one is linearly dependent on another, this actually is exactly the same thing. Now, so let's assume that our system of equations is linearly dependent. It means that there exists u and v such that the combination of the left part will give me 0 with these coefficients. Now, what does it mean? Now, by the way, it should be equal to 0 with any value of x and y. That's what it means, dependent, as functions of x and y. Right, so basically I have u a plus bc x plus u b plus b d y is equal to 0. Now, this is supposed to be equal to 0, as I just said, for any x and any y. What does it mean? How is it possible that under any circumstances, whatever x and y take value, this is always equal to 0? Only in one case, when this coefficient is equal to 0 and this coefficient is equal to 0. So basically we have this interesting system, again, a system of two equations with two variables. Now variables are u and v. So my question is, when is it possible? When is it possible? It's possible only in this case. Now, what does it mean? Sorry, this is G. Okay, so I know that there is this particular condition. Now, I claim that I can actually find u and v from this particular equation. How can I do it? Well, we can do the substitution method again. We assume in the beginning that a is not equal to 0, so u is equal to minus vc divided by a. Substitute to this, and we will have minus B, C, V divided by A, right? That's what UV means. Plus VG, it's equal to 0. We know A is not equal to 0. So let's do the common denominator. And what do we have? We will have minus BC plus A plus AG V equals to 0. Now, if this particular thing, again, EG minus BC, is equal to 0, then we can find any value of V will actually fit. And then U can be calculated from this. Now, if however, AG minus BC is not equal to 0, then V must be equal to 0. And if V must be equal to 0, then U must be equal to 0. And obviously this is not a linear dependency, because yes, of course I know that 0 times this plus 0 times this would be 0. This is not a linear dependency. Linear dependency means that U and V are not together equal to 0. But again, if AG minus BC not equal to 0, then V must be and U must be equal to 0. So system would be independent. And if it is equal to 0, then we can find any number of values for U and V to actually make the system dependent. Well, that's actually the proof that this particular expression, AG minus BC, is a characteristic property of the system of two equations with two unknowns, which basically determines whether the system has or it doesn't have one and only meaningful solution. Okay, so the method of substitution works not only for the system of two, as I was just explaining, equations in the general form, but if you really want to exercise, you can do it with three equations of three variables and basically any n equations. The system works always, the method works always. You just have to be very, very careful and do all these steps sequentially. That's fine, no problem. Now, there is another method to solve system of equations. Now, this other method is called elimination, and it does require a little bit of ingenuity. It does require certain, observance, if you wish. Look at my system. There is some peculiarity in the system which I can use to get faster into the solution. Here is an example. I think that would be actually a very good example. X plus y plus z, same example as before actually. X plus 2y plus z equals 8, and 2x plus y is equal to 4. Now, here is something which I observed, I noticed. Subtract the first equation from the second. You see, x and x will eliminate each other, z and z eliminate from each other. Y minus y plus 2y would give you y is equal to 8 minus 6, which is 2, immediately. Right? So I didn't do all these manipulations, x expressed as 6 minus y minus z, substitute into others, etc. I immediately subtracted these two things, one from another, and got the solution. I just noticed it. You know, call it ingenuity. Now, if you substitute it here, you will immediately get that 2x is equal to 2, and x is equal to 1. So this is solution, this is solution. 1 and 2, 1 and 2, so this must be 3. Right? So z is equal to 3. This is a faster method. So sometimes you can notice that this particular elimination thing really gives you a significant saving in the time you have to spend relative to substitution method. But again, it does require certain observance, and obviously not every system of two equations can be, solved this way. But some of them can, and it's actually very interesting if you notice that there are certain systems which you will try to solve, and they do possess certain peculiarity which you can use, and use the elimination method to simplify your test. Here's another problem which is a little bit more, I would say, interesting. Okay, what's good about this system? It's kind of symmetrical, you see? Minus z, minus y, minus x. So it looks nice. I don't know if people feel certain aesthetical feelings about systems of equations, but if I would consider that there is some aesthetics, this definitely is part of it. It has certain cyclical symmetry, if you wish. How can I solve this particular equation just based on again, some peculiarity of this system? Here is something which I can suggest immediately. Summarize all three of them. You will have x plus x minus x, so you have 1x, y plus y minus y, 1y, and z plus z minus z, 1z. So if I will summarize all three together, I will get x plus y plus z equals to 4, 9. Does it make my life easier? Yes, of course. Because what we can do right now is the following. Look at the difference between this and, let's say, this. If I will subtract from this, I will subtract this, so I will have x and y both eliminating each other, and only z and minus z would be, so it will be z minus minus z equals 9 minus 1. So it's 2z equals to 8, and z is equal to 4. Right? Now, if from this I subtract this one, the second equation, my x and z would eliminate each other, and I will have only 2y. I would have y minus minus y is equal to 9 minus 3, which is 9 minus 3, which is 6 to y, so y is equal to 3. Now, finally, if I subtract from this the third equation, my y and z would eliminate each other, and I will have only x minus minus x equals to 9 minus 5, which is 4 to x, x is equal to 2. So, again, this is a simpler solution which is based on this particular method of elimination. I have noticed something peculiar about this particular system. Now, what's interesting is I would like to solve my original system of two equations, which the generalized one with a, b, c, and d coefficients. Can I solve it using this method of elimination? Now, I did tell you that there are certain peculiarities which you have to look for, and it's very interesting and important actually with system of many equations with many variables. But in case of two, it's actually quite easy to do this particular method of elimination. Now, how can I do it? Well, look, this is a times x, this is c times x. So what we can do is we can multiply the first one by c, the second one by a, and we will have exactly the same coefficient at x, which means we can then subtract it, right? So instead of this, we will get this. ACX plus BCY is equal to PC. And this one by A, so it's ACX plus AGY is equal to AQ. Now, if I subtract them, I will have only y, and the coefficient at y would be AG minus BC. Y is equal to AQ minus CP. from which y is equal to aq minus cp divided by ad minus bc. And if you will compare it with my method of substitution, it's exactly the same thing. But faster, as you see. So again, I have basically shortened my my solution. Now, if instead of this I will aim for elimination of y, I would have to multiply this by d and this by b and then subtract. So it will be adx plus bdy equals gp, and this by b it will be bcx plus bdy equals bq. Now I subtract them, my y will be nullifying each other, so I will have ad minus bcx equals dp minus bq, and x is equal to this divided by this. The same exactly answer as before. So, in case of the system of two equations, the method of elimination actually can work even in the generalized form. In case of bigger systems, it's slightly more difficult. But you can imagine that there are certain cases when it can be really done. All right, that's basically it about algebraic solutions. I would like to spend a couple of words about graphical solutions, and only in case of two variables. So if I have, again, generalized system of two equations with two variables, I can always think about the graphical representation of this and this. So if x and y are coordinates, then what is the representation of this and what is the representation of this? These are straight lines. Now, we were talking about graphs of the functions. These are straight lines. So any linear dependency between x and y constitutes a straight line. Now, two straight lines can either be parallel to each other, or they can coincide with each other, or they can intersect each other. Only in case of intersection, solution is one and only a unique solution to this system of two equations. Because on the first line, you have all the pairs of x and y which satisfy this particular equation. On the second line, you have all the x and y pairs which satisfy the second equation, and only in case these lines intersect each other in one and only one point, you can say that this point of intersection is coordinates of x and y, coordinates of the point, with coordinates satisfying both equations, this one and this one, because this intersection point belongs to both lines. Okay. Now, well, the question is, under what circumstances you have these two lines parallel to each other, or intersecting each other, or coinciding with each other? Well, coinciding is simple when these two equations are exactly the same. So if you have something like, well, the same, or they can be actually factored. So it's basically, if this is the first equation, if the second equation is Ka plus Kb, Kax, I meant, plus Kby is equal to Kp. So if C is equal to Ka with K some number, G is equal to Kb and Q is equal to Kp, but K is exactly the same factor. Obviously, K can be basically reduced, and you will have exactly the same equation twice. So these two lines, in this case, completely coincide with each other. Now, if they are not like this, but like this, where Q is not the same K multiplied by phi. So these are proportionate left and right, but the right sides are not proportional to each other. So these have certain proportionality and the right part is not. Then you will have two parallel lines. And only in case the left parts are completely linearly independent, then you will have one and only one intersection. Well, basically that's it. That's all I wanted to talk about systems of linear equations. I would recommend you to reread the notes for this particular lecture. They are on unizor.com in the corresponding section of algebra. Well, basically, good luck. Thank you.